Hi, and welcome back to my videos for General Chemistry 1. Today, we'll finish our trilogy of videos talking about the properties of atoms that we can predict using the periodic table. That'll make it possible for us finally to understand how atoms bond together and form molecules. That's a big step in helping us understand molecules and the way they react. As we mentioned in the previous two videos, we'll talk about 4 properties of atoms that are affected by the effective nuclear charge that the valence electrons of an atom feel. In those videos, we talked about the first 3, the atomic radius, the ionization energy, and the electron affinity. Today, we'll tackle the last property, the electronegativity. To understand what electronegativity is, let's start by imagining a fluorine molecule. You might remember from an earlier video that fluorine is a diatomic element, so a fluorine molecule consists of 2 fluorine atoms bonded together. From our discussion a few videos ago, you might also recall that the valence electrons in fluorine feel an effective nuclear charge of +7. So, when we make a bond between the atoms, the valence electrons in the bond feel an equal pull of +7 toward each nucleus. So, the electrons in the bond tend to be at the center of the bond, halfway between the 2 atoms. We can see that if we look at this model, which shows the distribution of electrons in the molecule. In this molecule, negative charges are in red and positive in blue. As you can see, the charge from the electrons is distributed symmetrically between the atoms. On the other hand, what happens when the atoms are not the same? Suppose we have a fluorine atom bonded to a carbon. The valence electrons in carbon feel an effective nuclear charge of +4, so the electrons feel a greater attraction to the fluorine atom. Again, if we color code the charges in the molecule, you can see that the electrons are closer to the fluorine than to the carbon. In this case, we say that the fluorine is more electronegative than the carbon. Electronegativity is a measure of the ability of an atom to attract the electrons in a bond. As you can imagine, it's related to the effective nuclear charge. It turns out that the carbon has an electronegativity of 2.544, and fluorine has an electronegativity of 4.193, much higher, so fluorine is a much more electronegative atom. Now let's look at one last example. Suppose we have a fluorine bonded to a lithium. The valence electrons in lithium only feel an effective nuclear charge of +1, so the electrons again feel a much stronger pull toward the fluorine. Once again, this model shows that the electrons spend more time near the fluorine, but the effect is even stronger this time. You can also see this by looking at the electronegativity for lithium, which is only 0.912. much smaller than the electronegativity of fluorine. As you might imagine, the electronegativity follows the same trend as the ionization energy, which we talked about in the last video. So the electronegativity is generally higher as we go up and to the right on the periodic table. The person who came up with the concept of electronegativity was one of the most famous chemists of the 20th century, Linus Pauling. Pauling was very interested in the bonds that occur between atoms, and even wrote one of the best books on the subject, which I even have a copy of. He and his wife Eva were also very concerned about ethical issues in science, and they were strong advocates of banning nuclear weapons. They were vocal opponents of the United States' involvement in the Vietnam War, which means Pauling was criticized by the U.S. Senate, which called him an activist for the, quote, communist peace offensive. But it also led Pauling to be awarded the Nobel Prize for Peace in 1962, and 8 years before that, he also won the Nobel Prize for Chemistry, which makes him the only person in history to win 2 Nobel Prizes in both a science and in another field. He won the prize in chemistry for his work with electronegativity and for his studies of chemical bonds, including the stuff we'll talk about next. So here are the 3 bonds we've seen so far. It turns out that these 3 examples illustrate the 3 different types of chemical bond that we'll be talking about in this course. When the electrons are mostly near the middle of a bond, we say that that bond is nonpolar. If the electrons are closer to one of the 2 atoms, we say that the bond is polar. Both polar and nonpolar bonds are two different types of covalent bond. And in this third example, the valence electrons are almost entirely on one of the two atoms, and that's called an ionic bond. So, how do we decide whether a particular bond is nonpolar, polar, or ionic? All we need to do is to look at the electronegativities of the two atoms. If the difference between the electronegativities is 0.5 or less, then it's a nonpolar covalent bond. If the difference is greater than 0.5 but less than 1.75, then it's a polar covalent bond. And if the difference is 1.75 or higher, then it's an ionic bond. So let's try some examples. Suppose we're looking at these different bonds. Let's try to put these in order, from the least polar to the most polar. To do that, all we need to know is the electronegativities of the atoms, which are these. So, we take the difference between the two atoms in each bond. If we do that, here are the differences. Now we'll just put them in order, and we find out that the carbon-sulfur bond is the least polar, and the calcium-chlorine bond is the most polar. We can also figure out whether these bonds are nonpolar, polar, or ionic. Remember, the nonpolar bonds have an electronegativity difference of less than 0.5. So the carbon-sulfur, carbon-hydrogen, and nitrogen-bromine bonds are all nonpolar covalent bonds. Polar covalent bonds have an electronegativity difference of between 0.5 and 1.75. So that covers the phosphorus chlorine, silver chlorine, and aluminum chlorine bonds. And finally, ionic bonds must have an electronegativity difference above 1.75. So only the calcium chlorine bond is ionic. The difference between covalent and ionic bonds is especially interesting. It turns out that molecules that consist of only ionic bonds are usually soluble in water, and molecules that contain only covalent bonds often aren't soluble in water. Also, molecules that contain only ionic bonds usually have a higher melting and boiling point than molecules with only covalent bonds. For example, the electronegativity difference between sodium and chlorine is 2.00, so it's an ionic bond. On the other hand, the bonds in a molecule of carbon disulfide have an electronegativity difference of just 0.244, so those are nonpolar covalent bonds. If we measure their boiling and melting points, we find out that sodium chloride has a melting point of 801 degrees C and a boiling point of 1,465 degrees C. In contrast, the carbon disulfide melts at a much lower, negative 111 degrees Celsius, and it boils at just 46.3 degrees Celsius. So the difference between ionic bonds and covalent bonds has a big impact on the properties of the molecules. Well, that's all for today. Next time, we'll take a closer look at the ways that atoms bond to each other through their valence electrons, and we'll start to understand the structures of molecules, including some pretty big ones that are important in living organisms. So until next time, have a good week.